following forms are an introduction to William Bricken. So let me start these forms. William Bricken has spent over 40 years developing the tools and techniques of boundary mathematics with computational applications to user interface, artificial intelligence, graphic programming languages, virtual reality, silicon architecture, semiconductor optimization, and most recently, iconic arithmetic. He has taught social psychology at State University of Victoria, education at University of Hawaii, software engineering at Seattle University, and currently mathematics at Lake Washington Institute of Technology. In industry, he contributed as a principal scientist at Advanced Decision Systems, distinguished fellow at Autodesk, software designer at Interval Research, and CTO of 2 startup companies, Stanford University MS, Statistics, and PhD Mathematical Methods of Research. Ladies and gentlemen, please welcome William Bricken.
Well, it's a great pleasure to be here. I've got 25 packed minutes to talk about exploring laws of form applied to arithmetic and algebra. The goals are to do arithmetic as closely as possible to the laws of form, and then use that to learn how to think using distinctions rather than numbers. So we'll look at 2 systems today. Unit ensemble arithmetic is directly influenced by Lou Kaufman. I added parallelism and dynamics to his work. And James Algebra is a collaborative work I did with Jeff James. We're also building on the numeric work of Spencer Brown and Jack Engstrom and many others. And I'm following Stephen Wolfram's pioneering idea that we can explore fundamentally different ways of thinking about math. The presentation's intended to be very simple and visual. Iconic forms look like what they mean, but it is a foreign language compared to the symbolic systems that we've all memorized. So first, unit ensemble arithmetic. And the founders of formal arithmetic over 100 years ago had a very different concept of arithmetic than what we teach in schools today. For them, numbers were simply tallies. And tally arithmetic is iconic. The representation of the number 4 is 4 units or 4 marks. And a number in general is an ensemble of all of that many identical units. Addition is just putting tally groups together. The sum looks like the combined parts. And addition, used to be called fusion. Fusion can be achieved just by the cognitive act of ignoring boundaries. It's like changing our focus, involves very little effort. Multiplication was exchanging units for entire ensembles. And the important idea here is that the operations of arithmetic are entirely independent of the process of counting. Doing arithmetic's real simple. Counting up the results takes all the effort. And a central problem, of course, with tallies is when the pile gets too big. Then we collect the tallies into groups and count up the groups. When we write numbers down today, those different groups are called place value. In contrast, depth value collects groups at different levels of nesting. And we can do this with iconic distinctions because they have an inside and an outside. So there's accumulation on the outside and grouping on the inside. Now we need 3 tools to manage magnitude. We make groups of a specific size. That's called the base. We all use the base 10 system. That means 10 on the outside is the same as 1 on the inside. Boundaries multiply contents by 10, or more generally by any base that we decide. Then we need to put these groups together to merge them. And we also need to be able to cancel out tallies that are heading in opposite directions, what we call the positive and negative numbers. So the reflect rule collapses opposite pairs out of existence. And iconic forms also have many physical and spatial dialects. There's enclosures like Spencer Brown's mark. There's physical blocks and trees and graphs and maps and rooms and paths. And so for our first demo, like the laws of form, there's no zero, empty distinctions are units, containment's the only relationship, and unlike text and speech, we're not constrained to sequential communication in time as well as in space. But unlike laws of form, arithmetic needs to accumulate tallies. So one mark is not the same as 2 marks. We also need to define the size of groups. I'll use base 2 in some of the demos. It's easier to see. That means 2 things go together to make a group. So here's an enclosure-based dialect with grouping of 2 and containers that merge. We'll add binary 7 at the bottom, excuse me, and binary 5 at the top, and the result is binary 12. And so here's multiplying 5 by 7. Each unit of 5 is replaced by the whole of 7. And now at this point, the multiplication's done. All the rest is just grouping and merging to make the result easier to count. And here's 35 divided by 7. We unmerge groups inside 35 until we get to the pattern of 7, and then we turn that into a unit. And what's left to be the binary representation of 5. So here's a network dialect. The bottom is the unit, and the top is the value of the network. We add networks by joining tops to tops and bottoms to bottoms. So here's 7 and 5 added. And at that point, we are finished with the addition. Now it's a bunch of grouping and merging. There's some merging. There's a grouping, another merging, another grouping. And now we'll multiply 5 by 7. Multiplication is just stacking the networks on top of each other. When the stacks are joined, the multiply is done, and the rest is grouping and merging. And that's 35 in binary. So here's a spatial calculator. It works just like a regular calculator, but it shows you the iconic process of doing the computation. This calculator uses a container dialect shaped like rectangles. Now, you know, in iconic arithmetic, there's no commutativity, there's no associativity, there's no zero, there's no addition facts that require carrying, there's no place value. And I share Graham's astonishment that at least math education hasn't caught onto this yet. So here we'll add 2 4-digit numbers. And at that point, the addition is done. Now it's just cleaning up. The numbers will group into tens, form boxes or containers, and there's the result. Now, here's some smaller positive and negative numbers added together. There's no difference between positive or negative except direction. The negatives will eliminate themselves. Grouping and merging might later expose more cancellations, and we're left with negative 12. So here's a big subtraction using base 10 tallies rather than digits. And there's 7 levels of nesting here. Now, at this point, we have a mixed polarity number. You can't write that in textual notation. We can get rid of the negatives by unmerging one unit from a deeper group. And here's a bunch of positive and negative tallies added together. Lots of parallel activity here. It turns out there's only one left. And finally, here's base 2 addition. There's 8 occurrences of the binary 5. Again, lots of parallel activity, and we're left with the binary representation of 120. Okay, so that's handling magnitude. Now I have to address computation and all the mathematical operations, and that's James algebra. James algebra uses distinctions and patterns of containment instead of numbers and operations. There are 3 pattern axioms, and that's all you need for everything that, like most people learn about math. The 2 systems are compatible. Unit ensembles handle magnitude. James algebra handles the computation. And this design is what computer science calls a reduced instruction set. Doing a small number of simple things a whole bunch of times is better than doing something complex and sophisticated just a few times. That is, brute force beats finesse. For people doing math, not thinking beats thinking. These ideas are just patterns of distinction and how they work in the laws of from the laws of form. One of Spencer Brown's greatest contributions is the law of calling. Some apparent structures are the same as nothing at all. And I've been rather extreme about this position. Nothing is not something. Void has no properties, doesn't support any concepts or relationships. With that perspective, several wonderful structural properties arise. Forms become unities with an outermost boundary. All forms are independent. And with containment being the only relation, the properties of forms are the properties of their containers. Forms that are defined to be equivalent to nothing are illusions. We can insert the illusions anywhere, in any amount, at any time, without changing the meaning of any existing forms. Illusions can be used to simplify existing forms and then discarded when we're done with them. Now, James arithmetic has 2 types of boundaries. I use parens and brackets. Numbers and operations are all just patterns of containment. The empty parens is the unit 1, and I use both an open and a closed notation for the unit. Now, parens forms need to accumulate their numbers, so they must violate crossing and calling, which are transformations that condense. The bracket is not numeric. It follows calling and doesn't accumulate. And it also dominates any parens form. So when the 2 types are nested with one within the other, they're void equivalent. And here are the 3 pattern axioms of James algebra. Capital letters stand in place of any forms. And that's all we need to do arithmetic and algebra. Inversion shows that parens and brackets mutually cancel in any circumstances. Now, when we transcribe symbolic math into iconic form, it turns out the symbolic notation is just full of unnecessary inversions. And it's also very common to bring inversion pairs into existence to construct forms that then we can arrange. So here's inversion. Pairs of boundaries come and go as we choose. And here's arrangement. This is the only way that James forms can be made more or less complicated. Here's a visualization. Arrangement has two directions. Collecting makes several forms into one. Dispersing makes one form into several. And the complexity in any system, at least in math, in arithmetic and algebra, arises because an arrangement unfolds in both directions. Both of the other axioms address presence and absence, which is way easier to deal with. So here's collecting, and there's dispersing. Now, there's some mystery here. The third axiom is J occlusion. It's void equivalent, which means that that particular pattern has no meaning. J is an unusual imaginary constant. It shows up frequently within James forms. It's transparent. It doesn't make a distinction, but it's also not an illusion. And so here's what J occlusion looks like. You'll see it go away into the void and come back, and we can bring it in anytime. Now, I'll introduce an abbreviation for J occlusion for more comfort, a third type of container, angle brackets. The rule is called reflection, and reflection just makes it easier for us to read it and to understand the forms. But I do want to emphasize that the angle bracket's not a new type of container. It's an abbreviation, and three containers would just make the algebra way too complex. So here's reflection. Any form A can be brought in and out of existence. And reflection gives us kind of the feel that something's happening, but it is void equivalent, so nothing is actually happening. And finally, here's how equality works. Equality is defined by J occlusion. It's not separate like in laws of form. The move theorem shows how equality emerges out of the void.
And this is a little 5-minute warning or so.
Well, we started late. I've got another 6 or 7 minutes to go.
That's true.
And here's a cover theorem. Now, that's a slide we can skip. It just says that the primary organization of James algebra is a frame. Here's how James algebra matches laws of form. Arrangement is just like transposition, but the inner distinction is a bracket. Inversions just like reflection, but one of the distinctions is a bracket. J occlusion is very different. It looks like occultation, but the J completely occludes both the inside and the outside A. And dominions similar to integration. This theorem is important for defining how the bracket unit works. But the main difference between laws of form and James algebra is that James forms are impermeable. They can't cross over distinctions. That's how they accumulate. The distinctions in laws of form are semi-permeable. Forms can cross over from the outside to the inside. And so Spencer Brown carefully defines distinction as crossing from the inside to the outside. Semi-permeability is the rule of pervasion. Spencer Brown calls it generation. And it's what makes laws of form act like logic. So we'll do some math here. Let's see. First of all, there's some adjustments. Addition and multiplication don't exist as operations. They emerge. There is an interpretation of brackets and parens in conventional math as exponential and logarithmic functions. Parens is a kind of exponential. Brackets is a kind of logarithm. But notice that neither has a base. So there's adjustment. There are no bases in this system. We can include an explicit base if we need it. And translating between James forms and regular notation using exponents and logarithms gets really ugly really fast. Here's the sine function as example. You can see it gets ugly and the James form gets big. Excuse me. And the third and final adjustment is there's no inverse operations. Subtraction and division and logarithms and negative powers and roots and imaginaries are all taken care of by J-occlusion, highlighted here with the angle bracket. So here's some scripts for doing pattern-based arithmetic. Remember, you'll only see arrangement and reflection and inversion. Adding is just seeing things as one group. Subtraction is reflection into void. For times two, multiplication is arrangement by dispersal. That's by making more forms. You'll see a lot of nested inversion pairs being returned to the void. Division is dispersal for reflection. Here's 2 divided by 4. Fractional division is collection for reflection. And in collection, you'll see a lot of inversion pairs being created from the void. And that's the form of a reciprocal. Here's 4 squared, 4 to the power of 2. Exponential is dispersion twice. And we're left with 4 squared. And here's the logarithm of 8 in base 2. That would be a 3 because 2 to the 3rd power is 8. Logarithms are arrangements collected 3 times. The layout's not linear. It's in featureless space. We can put the forms anywhere as long as we don't violate the containment relations. And a reflection gets rid of the explicit base.
All right, we do need to start thinking about the Q&A in a little while. When you're ready, you can conclude, sort of.
Got one more.
Okay, cool.
And so here's algebra. This is solving the general quadratic equation. That's the script. Here's the computation. Again, you'll only see arrangement in inversion and reflection. First, we make a parametric change here. Those are forms that have shown up in the James form. It's not anything, it's just common occurrences of structure. And now there's just a lot of arrangements trying to isolate X. And now we're done. To get to X, we just do a lot of move and cover operations, strip it down. And now there's a single X, and that is the James form. If we translate that, it looks like that in standard notation. It's quite unusual. Usually we put Y to 0 That's just to make it simple for computation. And that's the result. So yeah, there are more surprises, but I'm not surprised that we're out of time. I'll post some stuff later, the longer version. I'll show you a single calculus derivative that works for all algebraic functions, how to think about fractions of polarity rather than positive and negative. There's a quantized trigonometry, an organization for indeterminate expressions, and more about the mysterious fundamental constant J, which can be interpreted as the logarithm of -1. So, it's a challenge to present different ways of doing arithmetic because we've memorized so much since we were 4 years old. But here we're just having some fun with some patterns. All of the unit ensemble stuff is in the Iconic Math website, and all of the non-video content is in the Iconic Algebra books. And I hope we have some time for questions.
Yeah, so let's open it up for questions. Andre, hang on 1 second. There's one in the room back here. Hang on.
I just want to know, how is it that does Iconic Math, so if it's built on a single containment relation, does it, can it be shown, develop maybe, well, this is the first question, develop, shown maybe in like years time from now that all of the mathematical structures and everything, like the incompleteness and all of that, that can be parallel developed in this system? And the other question is more of like an ethno-mathematical question. Does Iconic Math, since it's post-symbolic, sort of, I want to say, democratize math a little bit? You know what I mean?
Let's see. Gee, I have to remember 2 questions at once. I'll do the second one first. I believe that the symbolic approach to math, which is very new, it's about 150 years old, is just a transient. But changing the inertia of a universally accepted form is going to be hundreds of years. It's not going to happen easily. We have done all of, come pretty close to doing all of finite math with just the mechanisms you've seen. Of course, some of them are just bootstrapped, but if you can do the quadratic equation, you can do all the polynomials. Logarithms and exponents and transcendentals are all built in. It's pretty easy to get to most of finite math.
All right, thanks. Yeah, so Andre, you go ahead and then.
Yes, thank you very much. This was very, very inspiring. I was totally taken about the simplicity of this iconic form. I'm a little bit puzzled with this J rule, but maybe I have to think it a little bit more over. But my question would be, do you have any comment on how to construct real numbers like with Dedekind cuts or with Cauchy follows?
Yeah, so to get it simple, we have to make some compromises. And one of them is that we can do transcendental numbers, but not arbitrary real numbers. And this is in respect to Wittgenstein. There are undescribable real numbers, and you can't get to them, you can't use them because you have no description of them, so we don't do them. So the real number field is partial depending on whether or not you can actually define what you're talking about.
Thank you.
All right, so.
No, unfortunately, I think we're out of time, but that was really cool. And thank you very much, William Bricken.